Hello guys, in this video we will see how to simulate an Orificemeter using ANSYS Fluent, and we will see the results. Then we will compare the results of the CFD with the conventional equation derived from Bernoulli's equation. As we all know, Orificemeter is an instrument used to measure the flow rate in a pipeline. Since the physical setup of an Orificemeter and a pipeline is axisymmetric, we need not to model the entire 3D model. We can model only the half cross section of this, and we can have an axisymmetric model. Let's take a pipeline which is having a diameter of 60 centimeters, and we have taken an orifice plate and that is having a diameter of 30 centimeters, that is 0.5 times of this diameter, and the 15 centimeter will be the length of this plate from the wall. And for our simulation we have taken 4 times of the diameter length at the upstream side and 6 times of the diameter in the downstream side. So these are the dimensions that we are going to use. And let's calculate the flow rate based on Reynolds number. We know that Reynolds number is equal to rho Vd by mu. Rho is density, V is velocity, diameter by dynamic viscosity. Let's take a laminar flow which is having a Reynolds number of 200. So this will be the value of the velocity for a diameter of 0.6 meters, that is 60 centimeter pipe that we have seen earlier. Let's start our simulation. First open ANSYS workbench. Once the ANSYS workbench is opened, click and drag the fluid flow fluent system into the workbench. Right click the geometry and open the design modeler. Okay, once you see the design modeler screen, we can start sketching. Ensure that you are drawing in XY plane because we have to use the axisymmetric model. Geometries in other planes will not be supported in axisymmetric model. Click sketching and make the plane normal to you. Change the units to centimeters. Now draw a rectangle. This corresponds to the pipeline, and the length of the pipeline is 240 plus 360, 600 centimeters, and the diameter of the pipeline is 60 centimeters. Since we are using axisymmetric model, we have to draw half of that. Go to dimensions. The length is 600 centimeters. Zoom to fit, and the radius of this pipe is 30 centimeters. Then let's draw the orifice plate inside this. Let the plate be very thin, so let's give a dimension of 0.1 centimeter for that. And we have to locate the position of that orifice plate. That is a 240 centimeters from the inlet of the pipe. Go to dimensions, distance from this line to this line, that is 240 centimeters. And the height of the orifice plate is 15 centimeter on one side. Go to general dimensions, right click and box zoom. This dimension is 15 centimeters. Then again zoom in and trim this out. Go to modify. Okay, now we have defined the dimensions. Let's change the sketch to a plane. Concept, surface from sketches. Select the base object and apply and click generate. Now we have created the geometry for our analysis. Let's close this and double click the mesh to create the mesh and define the names of the boundaries. Now the geometry is imported in the meshing module. Let's name the boundaries. Actually this is the axis of our pipeline, so click that and right click, create name selection and name this as axis. This is the inlet of our pipeline. Click that, right click and click and give name selection. Name this as velocity inlet. This is the outlet of our pipeline. Name that as pressure outlet. Then click the mesh and give an element size of 0.02 meters and click generate. Now the mesh is generated. Now we can close this meshing module. Right click the mesh and click update. Now double click the setup to open the ANSYS Fluent, where you have to define the boundary conditions and material properties. Just leave the default options and click start. Now the Fluent model is opened. You can see the mesh and the inlet boundary and the outlet boundary. In the general, change the 2D space to axisymmetric. Go to models, double click the turbulence model and change that to laminar, because we have selected a velocity that is based on Reynolds number of 200. Go to materials and fluid. Here we have only air. Double click the air. To import the water, go to Fluent database. Straight away go to the bottommost and select water liquid and copy the properties. Now we can close. Water liquid is imported from our library. Double click and change the properties as we have used in our calculation. Go to cell zone conditions and define all the fluid body as water liquid. Then you close it. Go to boundary conditions. The axis is already defined as axis since we have given the name selection, and inlet is also defined as velocity inlet. Double click and provide the magnitude of the velocity. As we have calculated, the velocity for a Reynolds number of 200 laminar flow is 0.00033 meter per second. Click apply and close. And at the outlet, just leave the atmospheric pressure. So let's leave as it is. Go to initialization and click initialize. Then click run calculation and just give a number of iteration as 100 and click calculate. It will take some time to converge the solution. Now the calculation is complete. You can see the solution is converged at 24th iteration. Now let's see how the velocity and pressure is varying inside the domain. Go to graphics, double click the contours. Let's see the pressure plot. Display the contours of pressure and click display. Here you can observe at the inlet the pressure is high and the pressure is dropped after hitting this orifice plate, and this pressure drop within this region will give us the discharge based on our calculation. Let's see that. Before that, let's see the velocity plot and let's move on to the calculation. This is the pipeline that we have selected for our analysis. Here we have to measure the pressures at 2 points, one at here and another at here. So this pressure difference will tell us the flow rate. In order to measure the pressures at that position exactly, we have to create a line at this particular place. So here the x distance is 120 centimeters and y distance is 0. Here this x distance is 120 centimeters, whereas the y distance is 60, because the diameter of this pipeline is 60, we have drawn this model exactly from the origin here. So here 0, 0 is there. So let's create this line in this in ANSYS Fluent to view the pressure result. Go to surface, create line or rake, name this line as upstream. X0, Y0 is 120, 0, and the XY locations for the second point is 120, 60. Everything is in centimeters, so let's go to the units, drag and navigate to length. Change the unit to centimeters. So X0 is 120 and Y0 is 0. X1 is 120 and Y0 is 60. And now we are creating a line at the upstream. Then we have to create another line at the downstream. Here the coordinate for the first point is 270, 0. And the coordinate for the second point is 270, 60. Now let's create the line for downstream. Now let us see the pressures at the locations that we have created. Go to contours, switch to pressure, and view the pressures at the upstream and downstream. That will be here and here. Save and display. And this is the value of pressure at the upstream. Right click the contour and you can see the value there, that is around 0.00163, and this is the pressure at the downstream, that is around minus -0.000377. Let us take these two values for our computation. These are the pressure values at the upstream and downstream respectively. And we know the formula for calculating the discharge, that is derived from Bernoulli's equation. A0 A1 is the area of orifice and the pipeline, and H is the pressure head difference that we have seen now, that is pressure at the upstream minus pressure at the downstream divided by density into gravity. Let's calculate that, and that pressure head, drop in pressure head comes to a value of 2.02 10 to the power of -7, and A0 and A1 are the areas of the orifice. Pi by 4 d naught square is the orifice diameter and the pipe diameter. Let's substitute the area values and also the head value that we have calculated, head loss value that we have calculated, and this theoretical equation gives us a value of 1.46 into 10 to the power of -4 meter cube per second of volume flow rate or discharge, and this corresponds to 0.146 kilogram per second of mass flow rate. That means we have multiplied the density in order to get the mass flow rate. And now let us see what is the actual mass flow rate. We have given a velocity and we have given the area at the inlet. So based on that, the Fluent will compute the actual velocity or actual flow rate at the inlet. So let's see that. Fluxes, mass flow rate at the inlet. We have given a value of velocity. The same value is converted to mass flow rate simply by using the inlet cross section, and this is the actual flow rate, that is 0.094 kilogram per second, and there is a deviation, and this is the value that we have calculated using this expression. This is the theoretical one, and the actual discharge is something different. So that is called coefficient of discharge. that is equal to actual discharge divided by the theoretical discharge. That comes around 0.64. This is the typical coefficient of discharge value for an orifice meter. Thank you for watching this video. If you have any comments, please feel free to post it. Don't forget to subscribe.